So, welcome back for the last time now for this course, and I hope you have enjoyed and you have more importantly learned something. And this is a fundamental course for chemical engineering students. So, whatever you do in your life, you actually have to learn the core subject well, and based on that you can expand into any discipline in future what you want. Chemical engineers actually have been one of the most chemical engineering has been one of the most versatile disciplines. Of course, there is a lot of potential in the core, but you can do a lot of things outside also. So, that sort of brings us to the last lecture of the course, and we will discuss on psychrometric chart, which we started in the previous lecture. Any feedback or anything you want to know which is not clear. So, when the course is running, of course, there will be the live sessions where you can take advantage of interacting directly with me. I will try to clarify your doubts. But even other than that, if you are listening to this lecture, because these lectures will be available in YouTube and all that, and if you have any doubt, so please feel free to email me and I will try to respond. Okay. So, with that I sort of start the last lecture, and this class, or all of you who have been following this class rigorously, now you should not be having any difficulty in understanding this rather complicated looking graph, which we now know is the psychrometric. It is psychrometry. Please do care that there is an R, which a lot of people tend to miss out. Okay, so, now what are the things we know? So, x axis actually is the dry bulb temperature, y axis is the specific humidity, right, or the moisture content, and then some of the lines we understand. So, these set of inclined lines are the wet bulb lines, and at the end of the wet bulb line it is written 30%, 30, 20, 20, 35, 40. So, these are the wet bulb temperatures, and when in the previous lecture I was telling you that these two temperatures are same, obviously, because this is the 100% saturation line. So, on the 100% saturation line, of course, so this is up to 90% and this is a saturation line. So, of course, if this is 30 degree, you go down and you see this is also 30 degree, because at saturation the wet bulb temperature and the dry bulb temperature are same. So, we now understand four stuff. So, these are the wet bulb lines and the relative humidity. So, it is like 1%, 2%, then 10, 15, 20, 30, 40, blah blah. But in addition to that, there are three other parameters which I highlighted. So, this parameter is enthalpy at saturation, kilojoule per kg dry air. So, let us mark this as 1. This is enthalpy at saturation and unit is kilojoule per kg dry air, right. So, this is enthalpy at saturation. So, if you have air, let us say this is the condition of your air, right, then you automatically can find out what is the enthalpy at saturation. So, per kg of dry air, its enthalpy of saturation is 144 or 143 or whatever. I cannot see that clearly, right. So, it is like 143 or whatever, you can find it out. But then comes the question, if you have humid air, right, which is not 100% saturated, you can't use it because this is at saturation. So, there is something that you can use, and for that you have these set of lines. You see this nearly vertical, but slightly curved lines you have, right. These are the third set of lines actually. There are three sets of lines. So, these dry wet bulb lines we now know, right. So, these we know very well now, but you see there are this nearly vertical, but slightly curved lines, and of course, the x and y axis are the dry bulb lines and the specific humidity lines. And here you see what is written is enthalpy. Let me just see what exactly is the terminology they have used. It is enthalpy difference or something like that. So, what it means is some numbers are written over here. So, this is minus 4, right. So, this is minus 5, this is minus 4, this is minus 3, this is minus 2, this is minus 1, this is minus 1, this is minus 1.5 and things like that. So, instead of being at saturation, let us say if you have a condition over here. So, how do you find out its enthalpy? Enthalpy of this humid air you can find out. So, you find out the enthalpy at saturation, follow the wet bulb line, right, and from there now you see how on which enthalpy deviation line it lies, and you find that this is very close to minus 1.5 line. So, this is minus 2 line. So, now what you can say that the enthalpy of the unsaturated air, whatever that is, right, it is the unsaturated air based on this condition, and condition also you can find out. So, this has specific humidity of 0.0305 0305 and dry bulb temperature of 58 degrees centigrade. That is the point. So, you can straight away say that its relative humidity is 25%, its wet bulb temperature is 37 degrees centigrade, but in addition to that you can also say its enthalpy is 143 minus 1.5, that is 141.5 kilojoule per kg dry air. So, again I will repeat, how do you get the number minus 1.5 or whatever. So, first you look into this point, from here you find out, you follow the wet bulb line, find out the enthalpy at saturation, then you find out the nearest enthalpy deviation line, which are these lines, and here we find it lies close to minus 1.5. So, it is like 143 minus 1.5, it is 141.5. So, enthalpy at saturation we understood, this enthalpy deviation I am unable to read exactly what is written in this particular chart, does not really matter, but this is what is the function of it. The third set of lines is these lines. So, where you have these numbers 1.15, 1.20, 1.10, 1.05, then you have 1, then 0.95 and things like that. This is a third set of line. These are also slanted lines, but at a much lower, higher slope as compared to the wet bulb lines, and these are essentially, these lines are, as you can see over here in this enlarged or the magnified version, volume, these are the humid volume essentially. So, this is essentially the volume of air, the humid air, meter cube per kg dry air is the specific volume or the humid volume. So, these are the third set of lines. So, these are the third set of lines, third type of lines. This gives you the humid volume. So, you actually, if you can point, you can identify one point. So, one point on the chart, from there you can get 4 different entities. So, firstly wet bulb, dry bulb, relative humidity, specific humidity, these 4 obviously. Then you also get humid volume and the enthalpy, right. So, these 6 terms, so just look at one point and you get 4 more. So, you can essentially have a combination of any 2 to locate a point on the psychrometric chart, and then the remaining 4 you can straight away find out. So, let me tell you, like we have a condition like the specific enthalpy, the specific humidity is 0.02 and the relative humidity is, let us say 80%. Can you do that? So, here is the 0.02 and this is the 90%, 80% line. So, you need to locate, of course, it becomes a little clumsy, but nonetheless. So, here is the point, 0.02 is the humidity, the specific humidity, and 80% is the relative humidity. So, straight away you can find out the temperature, which is 28 degrees centigrade, the dry bulb, wet bulb temperature is 26 degrees centigrade. Dry bulb temperature and wet bulb temperature very close to each other means that the system is very close to saturation, right. So, these things you can clearly understand. So, I hope now you can sort of locate points on the psychrometric chart quite easily. Now, let us quickly take up a few very interesting problems which you can also locate or do on the psychrometric chart. So, let us say humid air with specific humidity 0.04 and 80 degree centigrade is cooled to let us say 40 degree centigrade. What is the change in number 1 percent relative humidity and number 2 wet bulb temperature, number 3 amount of water condensed, right. So, let us see how what is specified. So, what is specified is that humidity, the specific humidity is 0.04 and the dry bulb temperature is 80 degree centigrade. So, here is 80 degree centigrade and this is 0.04. So, you go like this. So, I guess this is the point, right. So, this is the point. So, this is the initial point, point 1 let us say we mark. So, we find initially what we have is the percentage RH is somewhere again between 10 and 15%. So, let us say it is about 13%. The wet bulb temperature is somewhere between these two lines. So, it goes and hits here. So, it is 41, 42, 42.5. And it is said that it is cooled to 40 degree centigrade and HSP I must specify remains at 0.04 or it is sort of it is cooled to or it is simply cooled to 40 degree centigrade. So, if you just say that you have simply cooled it to 40 degrees, so what do you mean? It means that the dry bulb temperature has gone down. So, if the dry bulb temperature has gone down, so this is the path it is going to follow, because this is in the direction of reduction of the dry bulb temperature, and you see that it hits 40 degree centigrade somewhere over here, right. No, not there, sorry, I made a mistake. No, I think I am right. So, it is over here. So, now you see the wet bulb temperature. So, the final wet bulb temperature has now changed to 37 degree centigrade. Sorry, I made a mistake over here. It is not percentage, it is 42.5 degree centigrade. So, wet bulb temperature has gone to 35 degrees, 37 degree centigrade, and the relative humidity has shoot up to 80%. So, you can see this amount of water condensed. Well, nothing has condensed because water has not got saturated, right. So, this is a type of problem you can very easily do. Next, another problem we can do is that air at HSP of 0.04 and at 80 degree centigrade is now mentioned to be adiabatically cooled, to 50 degree centigrade. Yeah, I am just changing the number for some reason. What is the change? So, adiabatically cooled. So, the first problem is over, where we just mentioned that it is cooled. So, if it is mentioned it is cooled, you just look into the change in the dry bulb temperature. Here what we are mentioning that air with this, let us say it is the same initial condition. So, let us try to locate the point first. This is the point. So, 80 degree centigrade and 0.04. So, this is the point, right. So, it is adiabatically cooled, it says adiabatically cooled to 50 degree centigrade. Now, what exactly is adiabatic cooling means? So, initially, so the problem is same percent, what is the change in the percent relative humidity, the wet bulb temperature and the amount of water condensed. And so, initial condition, since the initial condition is same even for this particular problem. So, you can again cross check, the initial condition is like, probably we took a wrong point in the previous case because of the mix up. So, this is a problem, particularly if you are doing it online, be very careful. So, we probably see the relative humidity is not exactly 13%, but it is close to 14%, right, it is closer to the 15% line. And the wet bulb temperature we calculated correctly 41, 42. So, it is around 42.5 degree centigrade. So, that is perfectly fine. So, maybe in the previous problem also we should check what mistake we did. Did we make a mistake? No, I think we took 13%, we should have taken 14%, it is fine. So, we can always do a correction, right. So, this is the initial condition over here, and now it says that it is cooled adiabatically. So, any idea what do you mean by cooled adiabatically? That means that instead of the cooling line following horizontally, right, the cooling line will now follow the wet bulb line, because the wet bulb temperature is under adiabatic condition. Wet bulb temperature is achieved under adiabatic condition, you know that. So, now the process actually propagates like this, following a line parallel to the wet bulb line, and when does it stop? It says it is 50 degree centigrade. So, when this line intersects the 50 degree centigrade dry bulb line, right, which will be somewhere over here, yeah. So, it is over here. So, then you stop, right. This is your adiabatic cooling. So, what we learned, that if it says that you are doing adiabatic cooling, then you are essentially following wet bulb line, right. So, then under the final condition, what are the things that have happened? And please do also understand that here HSP was 0.04. Since you have cooled it adiabatically, the H has also changed, and it has now gone up to 0.04. So, it is like 0.056, right. But since you are following a wet bulb line, there is no change in the wet bulb temperature. So, I do hope all of you have understood, these yellow lines have no meaning, actually this is the process. I hope all of you have understood what is meant by adiabatic cooling. So, if it mentions that you have adiabatic cooling, right, you actually follow the corresponding wet bulb line, and then you can also find out what is the change in the humid volume, this and that, which you can all do. So, here there is actually no change in the wet bulb temperature, because you are following a wet bulb line. So, where the wet bulb temperature remains constant. But what about the humidity? Humidity was initially at 14%, and here you can see that it has shot up to, let us say 68%, right. So, this way you can do the, or draw a process, right, draw a process on the psychrometric chart. About the third part of the question, again there is no question, because you have not attained saturation. So, only when you attain saturation, then the question of water condensing out will be important. Since you have not attained saturation, there is no question, right, of any water condensing out. So, water condensing out is 0. We will immediately come to an example of when this thing happens. So, this is like normal cooling, right. This is how the normal cooling looks. You sort of follow the same specific humidity, right. Specific humidity remains same, but as the temperature reduces, the water holding capacity of dry air progressively reduces, and that is why the relative humidity goes up. So, as temperature reduces, with the same amount of moisture present in the system, you are now closer and closer to saturation, and therefore, the relative humidity goes up. Okay. This is how it looks like. Now, let us take another problem which is very close to this initial problem we looked into, and let us say now instead of 40 degree centigrade, we are cooling we are cooling to, let us say, 24 degrees centigrade. No adiabatic cooling, we are doing a normal cooling up to 24 degrees centigrade. Same initial condition, we can take different initial conditions, but since this graph and particularly on an online PPT, it is a little clumsy. So, I do not want to change the initial condition. So, here we know this is the initial point, right. So, initial point again we have located based on HSP equal to 0.04 and temperature equal to 80 degrees centigrade, right. So, based on that we know the initial humidity is 14% and the wet bulb temperature is 42.5 degrees centigrade. So, now it says that it is cooled to 24 degrees centigrade. So, perfect. So, we know how to draw cooling now and we start drawing the line. So, we go follow the line, the specific humidity remains same and you cool all the way, but here you see that this temperature is 36 degrees centigrade. This temperature, if you see over here, is 36 degrees centigrade and you have been told to cool down to 24 degrees centigrade. So, what happens as you cool down? So, this is a very interesting problem, very interesting problem. This is not the final condition, sorry. So, as you cool down, with the amount of water present in the air, you attain saturation at 36 degrees centigrade. So, now it is 100% saturated, but you still want to cool it down, right. So, now what will happen? Now, the cooling trajectory will follow the saturation line. So, this is 20 degree, 24 degree up to here. So, you are cooling. So, this is the cooling line, but it has now two parts. The first part is a cooling till saturation is attained, and after that if you progressively cool, now what happens is you are cooling, but you are following the saturation curve, and consequently now what happens beyond this stage or during this phase, now there is a change in the specific humidity. So, initially the specific humidity which was 0.04 now drops to 0.018. So, for this problem the third part is very relevant. So, what you can say, 0.022 kg per kg of bone dry air water has condensed out, right. More importantly, what about the final condition? Final condition, your final dry bulb temperature is given as 25 to 24 degrees centigrade, but now you realize that water or the air is saturated. So, the dry bulb temperature and the wet bulb temperature are going to be same. So, dry bulb temperature now equal to 24 degrees centigrade is equal to the dry bulb temperature, and of course, this happens at relative humidity of 100%, right. So, now I guess all of you can understand the physics of dew formation in the early morning in winters. This is exactly happens. So, let us say you have 70% relative humidity air at daytime, and now at night because of the cooling, let us say the temperature drops from 30 degrees centigrade to 13 degrees centigrade, right. And so, maybe at certain temperature with that amount of whatever is the moisture that is present, right, it attains saturation, and if you now cool further, right, this additional amount of the water that is condensing actually appears in the form of dew, and therefore, this particular point is the dew point. So, the moment dew point, there is no curve or anything like that, but for a system like this, where the cooling is associated with attainment of saturation, you can locate the dew point also. Of course, I gave 3 representative problems. You can also in principle have a system where you do adiabatic cooling to such a temperature that you attain saturation, and in that case the graph will look like this. So, of course, beyond saturation, or in other words adiabatic cooling is only possible up to saturation is attained, because after that you cannot have adiabatic cooling. The moment it condenses out, there is actually net transfer of heat. So, if you strictly, if somebody asks you how much you can do adiabatic cooling, right, you can go only up to the level of 100% relative humidity. Please do understand that this part of the curve will not be present, but this will not be adiabatic, right. So, adiabatic cooling you can go only up like this following a wet bulb temperature. The other thing which I am not emphasizing, so if you have a point which I request all of you, and this graph I will tell the NPTEL team to share with all of you as a course material. Any point if you locate, you can also find out probably the other parameters, that enthalpy at saturation, what is the actual enthalpy and humid volume. So, this needs a little bit of practice. So, that sort of brings us to the end of this particular course, and all I will say is thank you. But more than that, what are the things we have learned? We have essentially learned energy balance, we have learned the basic pedagogy, the terminologies, what is a system, this and that. So, energy balance, first we learned energy balance without chemical reactions. And one important thing what we have learned here is estimation of parameters. Because many of you will ultimately say, sir, after doing all this we actually have done this, or MCPT T1 to T2, MCPT dt integrated from T1 to T2. But what this course has also taught you is how to estimate CP in certain cases. In the next part of the course, we learnt about thermochemistry, you can say. So, energy balance with chemical reactions. And if you would like to add, of course, while handling chemical balance without energy balance without chemical reactions, you probably have learnt rather well to handle how to handle the steam table. And please remember, as a last time warning of this as I end this course today, is that steam is not an ideal gas under any circumstances. So, please do not use, do not get tempted to use PV equal to nRT for steam, it is not an ideal gas. So, then we learnt about energy balance with chemical reactions, and we learned some nice concepts like heat of reaction. Of course, one thing we have not talked about, that is activation energy, which is fine. So, heat of reaction, and then we learnt terminologies like heat of formation, etc., etc. And the third thing we learnt is essentially the concept of humidity and how to handle so different forms of humidity, the concept of saturation, and most importantly, very important concept is the wet bulb temperature. So, here actually you have learnt, in mass transfer particularly, you will realize that if you understand wet bulb temperature, how it is measured, what it is, you actually understand quite a bit of very intricate phenomena, because it is not that easy to visualize the condition under which wet bulb temperature can be measured, right. So, of course, this is a preliminary course and I have taught it in that manner. And then finally, we learnt how to handle the psychrometric chart, which is my personal favorite, because you can have so much fun with the psychrometric chart, including locating processes. So, with that I would log off, and I'd like to thank all of you, and I do hope that you all had an enjoyable time, and all the best for your future. Thank you very much.